and or you can have a collar that can slide in the direction of the collar, but you have constraint perpendicular to that direction. So this also has a known line of action. And well, this is like a frictionless pin, or rough surface is like pin support, and also you have fixed support that you have constraint for any direction in two-dimensional or three-dimensional, and also you have actually couple constraints. Well, you in two-dimensional you just have one couple, which is actually along the direction out of the surface. So and in 3D case, you're going to have three moments. So in 3D case, you're going to have 6 constraints in 3 directions and 3 couples. Hey, is there any question about different supports? Okay. Let's move forward. So for a rigid body to be in equilibrium, you have 6 equations in 3D case and 3 equations in two-dimensional case. So we can start with the most general one. In 3-dimensional case, for a body to be in static case or in equilibrium, the forces along x direction, y direction, and z direction should sum to 0. So you generally have sigma f is equal to 0, which is in a vector form, but if you expand it in its components, then you're going to have 3 equations. And you have the same thing for moments. And in fact, if you take the moment of forces about any point in the space, if that object is in equilibrium, then these 3 equations hold. And for 2-dimensional case, you're going to have sigma sorry. I have trouble writing with the pen today. All right. So for 2-dimensional case, you just have the first 2 equations and the moment around axis Z, which is the axis out of the two-dimensional plane. So for 3D case, you have 6 equations, and for 2D case, you're going to have just 3. And well, you had 2 concepts for equilibrium of 2 force body and 3 force body. Let me see if I can. Okay, so for a two force body, let me go to the whiteboard. Imagine you have a component like this. I think I cannot use my pen today. You have an object like this, and then you're going to have 2 forces, F1 and F2. Then for this object to be in equilibrium, you have sigma m equal to 0 around any point in this space. So if you take, for example, this is point A, this is point B, then sigma m or about A should equal to 0. So then this force F2 should act along the line of action of actually it should be along line AB, and you could write the same for M about B, and so the line of action of F1 should also be along AB. And well, if you have this object in equilibrium, and if these two are in the same line of action, then F1 should be equal to minus F2. So this is a okay, so this was a 2 force body, and for a 3 force body, you should have 3 forces that act. Actually, you should have 3 concurrent forces. So they're going to intersect at the same point. Their line of action should pass through the same point with the same concept. If you take the moment around that point, then all of them should, the sum of all the moments should equal to 0. So that point of intersection actually is the point of intersection for all three forces. Or either you can have all of them in all of them parallel to each other. So you're going to have two cases for three body. In one, they're all parallel, and in the other, they're all concurrent. So let's solve an example for a beam and with 5 forces acting on it, and you have 2 supports, a pin support at A, and you have also a cable here, so you have a tension cable in BC. So this is a 2-case, this is a 2-dimensional case, and you're going to have 3 equations of motion which in equilibrium are equal to 0, and then you should have 3 unknowns for these 3 equations. So if you draw the free body diagram, in point A, you have, this is a pin support, so there are 2 constraints, one in X direction and one in Y direction. And you also have a tension here at cable BC. So you have 3 unknowns, and you should write 3 equations to solve them all. But well, no, you should always start with the simplest cases. So for example, here you can write sigma f of x equal to 0, and because there are no forces in the x direction, then ax should equal to 0. And for actually deriving the ay or f of bc, it is good to choose a point so that you would have only one unknown force in the equation. So if you take point B, then FBC is not exerting any moment around point B. It's just AY, and it's just AY that is exerting moment around point B. So if you write sigma m about B equal to 0, then you have to write the moment of all the forces around point B. You have 28 inches, 6 plus 8 plus 8 plus 6 for 15-pound force, 22 inches for 20, 14 inches for 35-pound force, and 6 inches for 20 pounds. And well, you should consider the direction of AY, because it is going to make a clockwise moment around B. You should have a minus sign here, and also you have the distance of 6 inches from force, actually from reaction AY to point B. So with this equation, you just have one unknown, and you can derive AY, and it is positive. So the direction of AY is in the positive direction. And then you can do the same. You can write the moment around point A, or you can write sigma let me see if I can write. Okay, so you can also have sigma f of y equal to 0, because you derived a y from the last equation. then you're going to have only one unknown, which is FBC. Or you can write the moment around point A, and this is good. If you do this, you can also check your answers. So if you write after you derive FBC from the moment around point A, then you can write sigma f of y to check whether that is equal to 0. So either you start with moment around point A, or sigma f of y equal to 0, and then check your answer with another equation. And this is basically the same as sigma m over b, but the distances are with respect to point A. So is there any question about this problem? Okay, no questions. Okay, let's go to next problem. Here we have a tension around two pulleys, which has diameter of 10 millimeter, or not diameter, the radius of each pulley is 10 millimeter, and you have a component that is attached to point C by a fixed support. So here you have constraints along two directions, and also you have a constraint for a couple. So you have three unknowns, and this is a two-dimensional case, and you have three equations. So we're going to find the reaction at point C for this system, which is in equilibrium. So if you draw the free body diagram, then you're going to have two forces, because it is a cable. It is going to be along the direction of the cable. 20 Newton force along the direction of cable in these 2 points, which was already there in the problem. And you have Cx, Cy, and Mc, which are unknown reactions. So to solve this problem, then it is best to start with sigma f of x. Well, it doesn't really matter, because you have actually, yes, you just have 120 Newton force along the x direction, so you can write sigma f of x, and then Cx plus 20. These are the only two forces that are along the x direction, would be equal to 0. So Cx would be minus 20. So the direction of Cx is actually toward left, because you have a minus sign. And you have sigma f of y. Again, you just have 120 force downward, so it is negative, and Cy minus 20 would be equal to 0. So Cy is 20 Newton, positive. And in order to get the last unknown, the moment, the couple at point C, Basically, you can get any point in this space to derive this, but if you take point C, then you would eliminate Cx and Cy moments around point C. So this would be the best choice. So you take the moment around point C, and you get MC. It is a counterclockwise moment. Well, we assumed this to be counterclockwise, so it doesn't really matter. You can get the actually get a clockwise moment, but at the end you're going to get the same answer. So MC plus 20 times 16 meter. So you have 10 millimeter radius here, and also you have 45 millimeter from line AB to C. So you're going to have 50, let me see, yes, I'm taking the distance from point C to line AB. So it would be 45 plus 10, it would be 55. So you would have 0.055 meter for this horizontal force, and you're going to have 75 plus 75 plus 10 for the vertical force. So you would have 0.16 meter. And well, both of them exert counterclockwise moments around point C. So both of them are going to be positive, and at the end you're going to get a negative number for MC. So actually the reaction that you have at point C is going to be clockwise. Okay, is there any question? No question. Which one? The distance from this vertical force to C? You have 150 millimeter from this line, the vertical line that passes through A to C, right? You have 275 millimeter distances. And also you have a radius for the pulley, right? And this is 10. So it is going to be 160 millimeter, right? Okay, and then you convert it to meter. Okay, let's move forward. Okay, you have a component attached to well, this is a three-dimensional problem. So you have a component ABF, which is attached to points G, A, H, J. So it is you have a pin support at A, or you can call it ball and socket joint, and also you have tension cables which are attached to points G, H, and I. So when you have tension reaction, actually when you have cables, you know the direction of the line of action of these reactions. So if you draw the free body diagram for this problem, then you're going to have three cable forces, TDH, TFJ, and TBG, with known direction. And also you're going to have three forces along the three basic directions, AX, AY, and AZ at point A, and you do not have any couple here because it's a pin support. So basically, you do not have any constraint about the rotation about point A. So you call it a pin support or ball and joint support. So here you have AX, AY, AZ, TBG, TDH, and TFJ. So you have 6 unknowns. And for 3D case, you have 6 equations. So, well, this is also stable structure because not all of the forces are concurrent, or not all of them are parallel. So you can actually derive 6 unknowns based on 6 equilibrium equations. Well, for in this case, that you have you know the direction of cable forces, but you do not know the magnitude, then you have to use the unit vector for these forces, as you have learned in the previous lectures. So, for example, for TBG, you have -12 in X direction. This is 12 inch, and you have a 9 inch in Z direction. So then you can easily derive the magnitude of BG by the equation that you take the square root of 12 squared plus 9 squared, and you get 15 inch for the length of vector BG, and you can get the unit vector lambda BG by dividing the vector BG by 15 inches. So you're going to do the same for all these cable forces, that you know the direction but you do not know the magnitude. So for DH, for example, you have -12 in X direction and 16 inches in Y direction, and there's no component in the Z direction for any of the TDH or TFJ. And so you can get the magnitude of DH and FJ, and then you can get the unit vector for each of these directions. And as you know, then you can write actually the force, which here it is so the notation is not right because you have to have a vector for the lambda BG is a unit vector, and this T should not be in bold case, so it is just a magnitude. So as you know, you have any vector equal to the magnitude of that vector times the unit vector along the direction of that force. So this is the right form. So this T should not be in bold case, and this lambda should have a vector sign. So this is how we're going to represent this unknown reactions here. Well, in this case, well, you have 6 unknowns. You have to be careful about the equations you want to write. For example, you cannot write any equation in the X direction. I mean, sigma f of X is equal to 0, but you're going to have one unknown AX, and also you're going to have 2 unknowns for these two cables and also this TBG, which has the X component. And this is the same for Y and Z direction. So it is better not to start with f of X, f of Y, and f of Z equilibrium equations. But if you take the moment around point A, then you're going to eliminate A of X, A of Y, and A of Z, and then you're going to have three equations because it is in 3D case. So if you take the moment around this by actually writing the vector equation of moment, which is m equal to m equal to r cross f. So if you take the moment around point A, which is equal to 0, this is going to be a vector equation that you're going to have three equations for three components. So well, you have TDH, TFJ, and TBG as the unknowns, and you're going to have three equations because you have eliminated A of X, A of Y, and A of Z by taking the moment around point A. Then you can easily solve it for each of the cable forces. So first you have to derive the distance vector from B to A for the force TBG, from D to A for force TDH, and from F to A for force TFJ. So this is also not right because it has to be DH. So this is the well, if you take the moment around point A, then you would not have the unknowns A of X, A of Y, and A of Z, right? So you would only have three forces, TFJ, TDH, TBG, around point A. So actually by choosing point A, you're eliminating A of X, A of Y, you're eliminating three unknowns. So you only would have three unknowns left. Is that clear? If you choose, no, there is no constraint for moments. Well, it is always easy to actually get the, well, you have a support here, you have a ball at A, and when you have a ball, then you can easily rotate the component ABF around A, but you cannot translate it. So then you're going to have three forces in X, Y, and Z direction, but you can rotate it so there is no constraint for the moment. But for example, if you have a support like this, then here you cannot rotate ABC around point C. So it is fixed at C. You cannot see any pinned shape support here or ball and joint. So you cannot actually rotate it. So you're going to have a constraint at that point for the moment. Yeah, is that clear? Okay, so you have R from B to A and force TBG, which you represented by TBG times unit vector along BG. And I have to emphasize one more time that this TBG is not a vector, it is a magnitude. So it is a scalar. And for TDH, you would have actually R from D to the distance vector from D to A. And for TFJ, you would have the distance vector from F to A. So you have all the unit vectors, you derived it based on the geometry. You have lambda VG, lambda DH, and lambda FJ. And then you have to calculate the cross product. For example, for the first cable force, TBG, you have RBA equal to 12I. This is the distance vector from B to A, or it's better to say from A to B because you're taking the moment around point A. So the distance vector should be from A to the point that the force is exerting on. So it is from A to B. So it is plus 12. And then so IJK 1200 for R from A to B. And you also have the lambda BG, which is calculated before, minus 0.AI plus 0.6K. So this is for TBG. For TDH, you have the distance vector from A to D, which is 12I minus 16K. And then you would have the unit vector lambda DH, and then you would have RF A to F, which is 12I minus 32. Well, you have 4 8-inch distances here, so minus 32 inches in the z direction. And you derive lambda for Fj minus 0.6I plus 0.8J, 8J. So you have these three for the first three equations. And you also have two external forces, minus 24 along negative y direction. And you should also calculate the distance vector from A to C and from A to E. And then take the cross product. So you do not have any unknowns here because you have the magnitude of the forces. These are external forces. So this is the main equation. And if you calculate these cross products, then you're going to have three components in X, Y, and Z direction. And you can, these are actually three separate moment equations. Actually, which the moment equations about x-axis, y-axis, and z-axis. So each of them should equal to 0 because the moments in equilibrium and the moment around any point in space should equal to 0. So for components in x direction, you would have this equation, and you would have something for j, and you would have something for k. Yeah. Actually, I uploaded the link for our last discussion, and I will do the same for this one. I also uploaded the slides for the last discussion class. Okay, so here we have 3 equations and 3 unknowns, and then you can get each of the forces. So each of the forces in 3 cables. So you still have 3 unknowns for reaction at point A for the pin support. So for that, after you derive the forces in 3 cables, then you can write sigma f of x equal to 0, sigma f of y equal to 0, and sigma f of z equal to 0. And well, basically you can write these 3 equations in compact form of a vector equation. So if you denote each force by its vector representation, for example, the force in cable BG would be the magnitude of that force, T of BG times the unit vector, then you're going to have 3 equations, and each of the components should equal to 0. So you would have 3 equations, and actually in each of these equations you just have 1 unknown. So it is much easier to derive the reaction forces. And finally, you can get all the unknowns for this. Okay, is there any questions? Okay, let's call it a day. Thank you. Have a good one.